Hello there, and welcome to the Sleepy Science Channel. Tonight we'll be exploring the invisible currents that flow around us, through us, and above us. The gentle force we call wind. It moves without being seen, speaks without making words, and shapes our world in ways both grand and subtle. Wind carries seeds across continents, carves mountains over millennia, and whispers through leaves on quiet afternoons. It is everywhere and nowhere, always present, yet forever changing. From the gentlest breeze to the mightiest storm, wind tells stories of motion, energy, and the restless atmosphere we call home. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm understanding of wind to carry you. Let's begin. The nature of wind. Wind is simply air in motion, flowing from high pressure to low. At its most fundamental level, wind is nothing more than moving air. Air molecules traveling from one place to another, seeking balance. The atmosphere above us is not uniform. Some areas hold more air molecules packed together, creating high pressure. Other areas have fewer molecules, creating low pressure. Nature abhors imbalance, and so air flows from regions of high pressure toward regions of low pressure, trying to even things out. This invisible migration of molecules is what we feel as wind against our skin. The greater the difference in pressure between two regions, the stronger the wind that flows between them. It is a simple principle, yet it drives weather patterns across the entire planet. Every breeze you have ever felt, every gust that has rustled your hair, is air seeking equilibrium, moving through space in an eternal dance of balance. Wind begins with the sun's uneven heating of Earth's surface. The story of wind truly begins 93 million miles away with our sun. Solar radiation streams toward Earth constantly, but it does not heat our planet evenly. The equator receives sunlight more directly, absorbing intense energy throughout the year. The poles receive sunlight at a steep angle, spreading the same energy over a larger area and receiving far less warmth. This creates a fundamental temperature difference across Earth's surface. Warm air near the equator becomes lighter and rises. Cool air near the poles becomes denser and sinks. The atmosphere, attempting to balance these temperature differences, sets air in motion. Warm air flows toward the poles at high altitudes. Cool air flows toward the equator, near the surface. This circulation, driven by nothing more than sunlight falling unevenly on a spinning sphere, is the engine that powers all wind on Earth. Without the sun's uneven heating, our atmosphere would be still and silent. The Coriolis effect bends winds across the rotating Earth. If Earth stood still, winds would blow in straight lines, from high pressure to low. But our planet rotates, spinning once every 24 hours. This rotation introduces a curious effect, discovered by French scientist Gaspard Gustave de Coriolis in the 19th century. As air moves across Earth's surface, the ground beneath it is also moving, rotating with the planet. In the northern hemisphere, this rotation causes moving air to curve to the right. In the southern hemisphere, it curves to the left. The deflection is subtle over short distances but dramatic over long ones. This is why hurricanes spin counterclockwise in the north and clockwise in the south. It is why winds circling high and low pressure systems follow curved paths rather than straight lines. The Coriolis effect is invisible, a consequence of geometry and motion, yet it shapes every wind pattern on the planet. It turns simple flows into spirals and transforms linear motion into the swirling dynamics we see in weather maps. global wind belts circle the planet in predictable patterns. The combination of solar heating and Earth's rotation creates distinct wind belts that girdle the globe. Near the equator lies the intertropical convergence zone, where warm air rises and creates a band of relative calm punctuated by thunderstorms. On either side, between roughly 15 and 30 degrees latitude, are the trade winds. These steady breezes blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. They were so named because sailors relied on them for transoceanic voyages, trading goods across predictable routes. Further toward the poles, between 30 and 60 degrees, lie the westerlies, winds that blow from west to east, dominating the mid-latitudes. Finally, near the poles themselves, polar easterlies blow from east to west, driven by cold, dense air descending. These wind belts are not rigid or unchanging, but they represent the average flow of air across the planet. They have shaped exploration, migration, and the spread of life itself. The trade winds enabled exploration and shaped human history. For centuries before engines powered ships, sailors depended entirely on wind. The trade winds, blowing steadily from east to west across the tropics, became highways of exploration and commerce. European explorers in the 15th and 16th centuries learned to harness these winds, sailing southwest from Europe to catch the trades, then riding them across the Atlantic to the Americas. The return journey followed the westerlies further north, creating a circular route. Christopher Columbus used this pattern. So did countless others who followed. These predictable winds enabled the age of exploration, the exchange of goods and ideas, and unfortunately, the slave trade as well. The trade winds carried ships laden with spices, gold, and human cargo. They connected continents that had been isolated for millennia. Entire empires rose and fell because of the reliability of these atmospheric currents. When you feel a warm breeze from the east in the tropics, you are feeling the same wind that filled the sails of history. Monsoons are seasonal winds that bring life-giving rain to billions. In large parts of Asia, Africa, and Australia, the word monsoon means survival. Monsoons are seasonal wind reversals, driven by the differential heating of land and sea. During summer, land heats faster than ocean. Hot air rises over the continent, drawing in moist air from the sea. This onshore flow brings torrential rains that replenish rivers, fill reservoirs, and nourish crops. Without the monsoon, much of India, Bangladesh, and Southeast Asia would be desert. Civilizations have organized their entire calendars around its arrival. Farmers plant when the monsoon begins and harvest when it ends. Cities prepare for flooding. Ancient texts speak of the monsoon's timing with reverence. When the monsoon is late or weak, drought follows, and millions suffer. When it is strong, floods devastate, but also bring fertility. This seasonal wind has sustained more human lives than perhaps any other weather phenomenon. Its rhythm, ancient and reliable, continues to feed billions. Sea breezes cool coastal regions during warm afternoons. Anyone who has spent a summer day near the coast knows the relief of the sea breeze. As the sun climbs higher, land heats more quickly than water. The air above the land warms and rises, creating a zone of lower pressure. Meanwhile, the ocean remains cooler, maintaining higher pressure. Air flows from sea to land, bringing coolness with it. This sea breeze typically begins in late morning and strengthens through the afternoon, sometimes reaching several miles inland. It brings refreshment to beachgoers and moderates temperatures in coastal cities. As evening approaches, the pattern reverses. Land cools faster than water, and a land breeze flows gently seaward through the night. This daily cycle of land and sea breezes shaped coastal climates for as long as land and ocean have existed side by side. It is a small-scale circulation, but for those who experience it, the sea breeze is a daily gift from the physics of heat and air. Mountain and valley breezes follow similar daily rhythms. Mountains create their own wind patterns through the day. During daylight, sun warms the slopes, heating the air in contact with them. This warm air becomes buoyant and flows upward along the mountainside, creating a valley breeze that carries air from lowlands toward peaks. Gliders and birds of prey often ride these rising currents in the afternoon, spiraling upward without effort. At night, the pattern reverses. Mountain slopes cool rapidly under clear skies, chilling the air beside them. This cold, dense air sinks, flowing down into valleys as a mountain breeze. These winds are usually gentle, more like whispers than gusts, but they can be felt distinctly in alpine regions. Campers in mountain valleys often notice the temperature drop as cool air settles around them after sunset. This daily breathing of the mountains, inhaling by day and exhaling by night, is one of the subtler rhythms of wind. Wind and weather. Warm air can hold more moisture than cold air can. One of wind's most important roles is carrying moisture across the planet. Air's ability to hold water vapor depends on temperature. Warm air has more energy, allowing water molecules to remain in gaseous form. As air cools, its capacity to hold moisture decreases. When air becomes saturated, water vapor condenses into tiny droplets, forming clouds. This is why your breath becomes visible on cold mornings. The warm, moist air from your lungs meets the cold air outside and can no longer hold all its moisture. Wind moves vast quantities of water vapor around the globe. It carries moisture evaporated from tropical oceans toward the continents. It lifts humid air up mountain slopes where cooling causes rain. It brings dry air from deserts, parching everything it touches. Understanding this relationship between temperature, moisture, and wind is key to understanding weather itself. Every raindrop that falls, every snowflake that drifts down, began its journey as water vapor carried by wind. Clouds form where rising air cools and moisture condenses. Clouds are born from the marriage of wind and temperature. When air rises, whether over a warm surface, up a mountain, or forced aloft by colliding air masses, it expands and cools. As it cools, its ability to hold water vapor diminishes. Eventually, it reaches the dew point, the temperature at which air becomes saturated. Water vapor begins condensing around tiny particles of dust, salt, or smoke, forming microscopic droplets. Billions of these droplets cluster together, and we see a cloud. The shape and type of cloud depends on how the air is moving. Gentle, widespread rising creates layered stratus clouds. Vigorous updrafts produce towering cumulus. Wind shear can stretch clouds into wisps and waves. Every cloud in the sky is a visible record of invisible air currents. They are wind made visible, sculptures of motion frozen momentarily in water droplets, revealing the hidden choreography of the atmosphere. Different winds create different cloud formations across the sky. The clouds above us are storytellers, revealing the winds that shape them. Smooth, lens-shaped lenticular clouds form when wind flows over mountains, creating standing waves in the atmosphere. Cirrus clouds, thin and wispy at high altitudes, are stretched into delicate filaments by strong jet stream winds. Cumulus clouds, puffy and heaped, form in rising columns of warm air. Stratocumulus spreads in lumpy sheets under stable conditions. Altocumulus appears in rows when waves ripple through the mid-atmosphere. Mammatus clouds, with their distinctive pouch-like protrusions, form in sinking air beneath thunderstorms. Pilots and meteorologists learn to read these signatures. A sailor might look at mackerel sky, rippling altocumulus, and know that weather is changing. The sky is a canvas, and wind is the artist, painting in water vapor and ice crystals, creating forms that last minutes or hours before dissolving into air again. Precipitation falls when cloud droplets grow heavy enough to overcome updrafts. Clouds do not automatically mean rain. The tiny droplets inside them are so small that even gentle updrafts can keep them aloft indefinitely. For precipitation to occur, droplets must grow larger. In warm clouds, they collide and merge, gradually building into raindrops heavy enough to fall. In cold clouds, ice crystals form and grow, eventually becoming snowflakes or hailstones. Updrafts within clouds play a crucial role. In gentle clouds, droplets fall as soon as they grow large enough. But in towering thunderstorms, powerful updrafts can loft droplets repeatedly, allowing them to grow into large hailstones before finally falling. Wind not only creates clouds, but determines whether they will release their moisture gently as drizzle or violently as downpour. The next time rain taps against your window, remember that each drop is the culmination of a journey through rising and falling air currents. Thunderstorms are born from powerful updrafts in unstable air. On hot, humid days, the stage is set for thunderstorms. Intense surface heating creates pockets of warm, moisture-laden air. When these pockets begin to rise, they find themselves warmer than the surrounding air and continue ascending rapidly. As they climb, they cool and condense, forming towering cumulus clouds. The condensation releases latent heat, adding even more buoyancy. The updraft accelerates, sometimes reaching speeds of over 100 miles per hour. The cloud grows taller, punching through the troposphere into the stratosphere, anviling out as it hits stable air. Inside, ice particles and water droplets collide, generating electrical charge. Lightning flashes, thunder booms, downdrafts develop, bringing cold air and rain crashing to the surface. A thunderstorm is essentially a battle between rising and sinking air, with wind as both weapon and participant. These storms can produce torrential rain, hail, damaging winds, and tornadoes. They are atmospheric giants, born from instability and sustained by the vertical winds within them. Downdrafts from thunderstorms can produce sudden, powerful gusts at the surface. One of the most dangerous aspects of thunderstorms is the downdraft. As rain falls through the cloud, it drags air downward. Evaporating rain cools the air further, making it denser. This cold, heavy air plummets toward the ground, sometimes at speeds exceeding 60 miles per hour. When it hits the surface, it spreads outward in all directions as a gust front. Anyone near a thunderstorm has likely felt the sudden blast of cold wind that announces the storm's arrival. This outflow can reach far ahead of the rain itself. In extreme cases, downdrafts concentrate into microbursts, violent columns of descending air that spread out explosively on impact. These can produce winds exceeding 100 miles per hour in a localized area, snapping trees and damaging buildings. Microbursts have caused airplane crashes, striking aircraft during takeoff or landing. They last only minutes, but their power is immense. These sudden winds remind us that the atmosphere, though invisible, carries tremendous force. Derechos are widespread windstorms, racing across hundreds of miles. Occasionally, a line of thunderstorms organizes into something larger and more sustained. A derecho is a widespread windstorm associated with a fast-moving band of severe thunderstorms. The term comes from the Spanish word for straight, distinguishing these straight-line winds from the rotating winds of tornadoes. Derechos can travel hundreds of miles, producing hurricane-force winds along their path. They form when a strong cold front or other boundary triggers multiple thunderstorms in a line. The storms feed off each other, their downdrafts reinforcing the system. As the line races forward, it can maintain intensity for hours, toppling trees, downing power lines, and devastating anything in its path. The damage swath can be hundreds of miles long and over 100 miles wide. Unlike tornadoes, which leave narrow scars, derecos flatten entire regions. They occur most commonly in the central United States during summer, but can happen anywhere conditions align. To experience a derecho is to feel the full, sustained fury of the atmosphere in motion. Tornadoes are violently rotating columns of air, reaching from clouds to ground. Among all wind phenomena, tornadoes hold a special place of terror and fascination. They form most often within supercell thunderstorms, where wind shear creates horizontal rotation in the atmosphere. Strong updrafts tilt this rotation upward, and under the right conditions, a funnel extends downward from the cloud base. When it touches ground, it becomes a tornado. Wind speeds inside can exceed 200 miles per hour, though most are weaker. The strongest tornadoes can scour pavement from roads, obliterate well-built homes, and hurl vehicles hundreds of yards. They vary wildly in size, from narrow ropes barely visible against the sky to wedge tornadoes over a mile wide. Their paths are erratic, sometimes lifting and touching down repeatedly. They last minutes to over an hour. The sound is often described as a freight train, a roar produced by wind and debris. Inside a tornado, pressure drops. Winds spiral inward and upward, and anything not firmly anchored can be lifted and carried away. Tornado Alley in the United States sees more tornadoes than anywhere on Earth. The Great Plains of the United States form a natural laboratory for tornadoes. Stretching from Texas to South Dakota, this region, known as Tornado Alley, sees more tornadoes annually than anywhere else on the planet. The geography is perfect. Cold, dry air from Canada meets warm, moist air from the Gulf of Mexico. The flat terrain allows these air masses to collide without obstruction. Wind shear, the change in wind speed and direction with height, is often strong. When conditions align in spring and early summer, violent supercells develop with alarming frequency. Residents of Tornado Alley grow up with tornado drills and storm shelters. They watch the sky with a practiced eye, recognizing the greenish tint and the ominous lowering of clouds that precede twisters. For meteorologists and storm chasers, this region is a place of both danger and discovery, where the most powerful winds on Earth spin briefly into existence before dissolving back into the storm. Waterspouts are tornadoes that form over water, appearing as graceful funnels. Tornadoes are not confined to land. Over warm, tropical waters and even temperate lakes, waterspouts form, creating graceful funnels that connect cloud to sea. Most waterspouts are weaker than their land-based cousins, forming in fair weather from rising columns of warm, moist air. They appear as slender tubes, often translucent except for the spray of water at their base. True tornadic waterspouts, spawned by supercell thunderstorms over water, can be just as violent as land tornadoes. Sailors have reported encounters for centuries, describing towering columns of spinning water and mist. Waterspouts can move ashore and become tornadoes if they cross a coastline. They pose hazards to boats and coastal areas. Despite their power, there is something mesmerizing about watching a waterspout dance across the surface of a bay or gulf, a temporary sculpture of wind and water, beautiful and dangerous in equal measure. Dust devils form in hot deserts, where intense heating creates spinning vortices. On a baking summer day in the desert, small whirlwinds often appear, spinning dust and sand into visible columns. These are dust devils, miniature cousins of tornadoes. They form not from thunderstorms, but from intense surface heating. The scorching ground heats the air directly above it, which rises rapidly. If there is any rotation in the surrounding air, perhaps from local wind shear or terrain, the rising column begins to spin. Centrifugal force tightens the rotation, and a dust devil is born. They are usually harmless, lasting only minutes, and rarely producing winds strong enough to cause significant damage. But they can startle hikers, sandblast vehicles, and occasionally reach impressive sizes. Dust devils occur in deserts worldwide, on Mars, where they have been photographed by rovers, and anywhere dry, hot surfaces meet light winds. They are reminders that wind can organize itself into spirals on many scales, from the gentle spin of a dust devil to the catastrophic rotation of a tornado. The jet stream and high-altitude winds. The jet stream is a river of fast-moving air high in the atmosphere. If you could ascend 6 to 9 miles above Earth's surface, you would encounter one of the atmosphere's most influential features. The jet stream is a narrow band of extremely fast-moving air, flowing from west to east in the mid-latitudes of both hemispheres. Wind speeds in the jet stream routinely exceed 100 miles per hour and can reach over 200. This high-altitude river of air forms at the boundary between cold polar air and warm tropical air. The temperature difference creates a strong pressure gradient, and the Coriolis effect concentrates the resulting wind into a narrow jet. The jet stream is not a single, continuous flow, but a meandering ribbon that undulates north and south, sometimes splitting and rejoining. It plays a crucial role in weather patterns, steering storms, influencing temperatures, and even affecting airplane travel. Pilots flying eastward seek the jet stream for a tailwind, shortening flight times. Flying westward, they avoid it, escaping its hindrance. The polar jet stream divides cold Arctic air from warmer mid-latitude air. The most prominent jet stream in each hemisphere is the polar jet. It forms where cold air from the Arctic or Antarctic meets warmer air from the mid-latitudes. This sharp temperature contrast, especially pronounced in winter, drives strong winds aloft. The jet stream acts as a boundary, a wavering fence separating cold from warm. When the jet dips southward, it brings Arctic blasts to lower latitudes. When it retreats northward, warm air surges poleward. The position and strength of the polar jet determine much of the weather experienced across North America, Europe, and Asia. A strong, fast-moving jet tends to keep weather systems moving quickly. A slow, meandering jet allows weather patterns to stall, leading to prolonged heat waves, droughts, or rainy spells. Meteorologists track the jet stream constantly, knowing that its behavior today will shape tomorrow's weather. It is an invisible river in the sky, but its influence is felt by everyone below. The subtropical jet flows at slightly lower latitudes year-round. In addition to the polar jet, a second jet stream exists at lower latitudes. The subtropical jet forms near 30 degrees latitude in both hemispheres, at the poleward edge of the Hadley cell circulation. Unlike the polar jet, which strengthens in winter and weakens in summer, the subtropical jet is more persistent year-round, though it is strongest in winter. It is generally weaker and less variable than the polar jet, but still an important feature of global circulation. Commercial airliners often use the subtropical jet for long-distance flights across the Pacific or over Africa. The existence of multiple jet streams adds complexity to the atmosphere's circulation. Sometimes the polar and subtropical jets merge, creating an exceptionally strong wind corridor. Other times they remain separate, each steering different weather systems. Together, these high-altitude rivers guide the flow of air, masses and storms around the planet, invisible highways for energy and moisture. Jet streams can steer hurricanes and influence their paths. Hurricanes are massive storms, but they are still subject to the steering currents of the atmosphere. In the Atlantic, hurricanes often form in the tropics and drift westward with the trade winds. But as they move north, they encounter the influence of the jet stream. If the jet is positioned just right, it can capture a hurricane and steer it northward, then curve it out to sea. If the jet is weak or positioned farther north, the hurricane may track westward into the Caribbean or Gulf of Mexico, threatening land. Forecasters watch the jet stream closely during hurricane season, knowing that subtle shifts in its position can mean the difference between a storm striking a populated coast or harmlessly dissipating over open ocean. The jet can also tear hurricanes apart. Strong wind shear associated with the jet stream can disrupt a hurricane's structure, causing it to weaken rapidly. This invisible wind high in the sky, far above the storm, exerts control over one of nature's most powerful phenomena. Clear air turbulence jolts aircraft in seemingly calm skies. Passengers aboard airliners occasionally experience sudden, jarring turbulence, despite clear skies and no visible clouds. This is clear air turbulence, and it often occurs near the jet stream, where wind speeds change dramatically over short distances. Waves and eddies form in the atmosphere, much like rapids in a river. Aircraft passing through these invisible disturbances can experience sudden updrafts and downdrafts. The effect can range from mild bumps to violent jolts that send unsecured objects flying. Clear air turbulence is difficult to detect because it leaves no visual signature. Radar cannot see it. Pilots rely on reports from other aircraft and on forecasts of jet stream positions. Advances in technology are improving detection, but for now, clear air turbulence remains one of aviation's hidden hazards. It is a reminder that wind, even high above the weather, can be unpredictable and powerful. The atmosphere is rarely as calm as it appears. Mountain waves can create smooth, powerful updrafts for glider pilots. When strong winds blow perpendicular to a mountain range, they create a phenomenon known as mountain waves. Air forced upward over the peaks descends on the lee side, then rebounds upward again, creating a series of vertical oscillations downwind of the mountains. These waves can extend for dozens of miles and reach high into the stratosphere. Under the right conditions, they produce smooth, powerful updrafts that glider pilots seek out. In these invisible elevators, sailplanes can climb to astonishing altitudes without engines, riding the wave like surfers on an ocean swell. The waves also create distinctive lenticular clouds, smooth lens-shaped formations that appear to hover motionless over mountains. These clouds mark the crests of the waves, where rising air cools and condenses. Mountain waves can also produce severe turbulence, especially in the rotor zone near the surface. What appears calm from a distance can be violently turbulent up close, a hidden complexity in the wind. Wind's effects on landscapes. Wind shapes sand dunes into waves across deserts. In deserts around the world, wind is a sculptor, patiently carving sand into dunes. Sand grains, too heavy to be carried far by ordinary breezes, saltate, bouncing along the surface in short hops. As they accumulate, they form dunes, which come in many shapes depending on wind direction and sand supply. Crescent-shaped Barshan dunes form where wind blows consistently from one direction. Long, linear Seif dunes align parallel to prevailing winds. Star dunes, with multiple arms, form where winds shift direction seasonally. Dunes migrate slowly, sometimes only meters per year, but over centuries they can bury forests, towns, and ancient ruins. The Pepe, the surface of a dune ripples with smaller wavelets. each a miniature version of the dune itself. Climbing a tall dune and watching the wind shift its surface is to witness geology in real time. The desert is never still. Wind ensures that sand is always moving, always rearranging, creating landscapes that feel both timeless and constantly changing. Erosion by wind carved the hoodoos and arches of desert lands. Wind does not only move sand, it also erodes rock, given enough time. In arid regions, wind-blown sand and dust act as natural sandblasters, wearing away softer rock layers and leaving harder layers behind. Over millions of years, this process creates stunning formations. The hoodoos of Bryce Canyon, tall spires of rock standing like sentinels, were shaped partly by wind. The arches of Utah, graceful spans of stone bridging empty air, owe their existence to wind and water working together. Wind erosion is slow but relentless. It carves grooves, undercuts cliffs, and polishes rock surfaces to a smooth sheen. In some deserts, wind has scoured basins down to bedrock, removing all loose material and leaving barren pavements. These landscapes are testaments to wind's patience. What seems gentle and ephemeral, just moving air, becomes over eons a force that reshapes mountains and valleys. Deflation removes fine particles, leaving desert pavement behind. In many deserts, the surface is covered not with sand, but with a mosaic of pebbles and stones called desert pavement. This arises through a process called deflation. Wind removes the finest particles, sand, silt, and clay, leaving behind only the coarser material that is too heavy to be moved. Over time, the surface becomes armored with stones, protecting the finer material beneath. Desert pavement can resemble a carefully laid cobblestone path, though no human hand arranged it. These surfaces are often ancient, undisturbed for thousands of years. Tire tracks or footprints can scar them for decades. Deflation also creates blowouts, depressions where wind has excavated loose material, and ventifacts, rocks sculpted and polished by wind-blown sand. In the harshest deserts, wind is the dominant force, more influential than water. It sorts sediments, redistributes them, and leaves behind landscapes shaped by its invisible hand. Loess deposits, wind-blown silt, cover vast regions and enrich soils. Not all wind-blown material stays in deserts. Fine silt and clay, lifted by wind during dust storms, can travel thousands of miles before settling. These deposits, called loess, blanket huge areas of the world. The central United States, China, and parts of Europe have deep loess soils, sometimes hundreds of feet thick. These soils are remarkably fertile, supporting some of the world's most productive agriculture. The Great Plains of North America and the farmlands of China's Yellow River Valley both owe their richness to wind-deposited silt. Loess is loosely packed and easily eroded, which is why rivers in loess regions, like the Yellow River, run thick with sediment. During the Dust Bowl of the 1,930 seconds, wind stripped topsoil from millions of acres, carrying it eastward in towering dust clouds. Some of that dust reached the Atlantic Ocean, falling into the sea. Wind, in moving soil, can both create and destroy agricultural heartlands. It is a force of fertility and a force of devastation. Coastal cliffs are worn away by wind and salt spray. Coastlines are battlegrounds where wind, water, and rock meet. Wind alone can erode coastal cliffs, especially when laden with salt spray and sand. The combination of salt crystallization and wind abrasion slowly weakens rock. Cracks widen, ledges crumble. Over decades and centuries, cliffs retreat inland. Sea stacks, isolated pillars of rock standing offshore, are remnants of former cliffs, cut off by erosion. Natural arches form where weaker rock is eroded away, leaving harder rock spanning the gap. Eventually, even these collapse. The wind's contribution is subtle compared to waves, but persistent. Salt carried by wind penetrates rock, crystallizes, and exerts pressure, fragmenting the stone. Wind-blown sand scours surfaces. Coastal erosion is a slow-motion transformation, each storm contributing a little more wear. Walking along a rocky shore, feeling the wind carry spray against your face, is to feel one of the agents shaping the edge of the land. Trees bent by prevailing winds reveal the dominant wind direction. In exposed places, coastal headlands, mountain ridges, open plains, trees grow leaning, their branches swept to one side. These are flagged trees, sculpted by prevailing winds. Buds on the windward side are killed or damaged by desiccation and cold, while those on the leeward side survive. Over years, the tree grows asymmetrically, all its branches reaching away from the wind. The effect is striking. Entire forests leaning in unison, permanent markers of invisible currents. In some places, trees grow stunted and twisted, crumholes, barely rising above the vegetation, their forms contorted by relentless wind. These trees are survivors, adapted to conditions few plants can tolerate. To see them is to see wind's influence written in wood. They stand as testimonies to persistence, shaped by forces they cannot escape, yet enduring nonetheless. Windbreaks of trees reduce erosion and protect crops and homes. Farmers and homesteaders have long known that wind can be both enemy and resource. To combat wind erosion and create sheltered microclimates, they plant windbreaks, rows of trees or shrubs positioned perpendicular to prevailing winds. These barriers slow the wind, reducing its erosive force and creating calmer zones downwind. Fields behind windbreaks lose less topsoil. Snow accumulates more evenly. Crops yield better. Buildings suffer less wear. In the Great Plains, after the Dust Bowl, farmers planted thousands of miles of shelter belts, transforming the landscape. Windbreaks also provide habitat for wildlife and can reduce heating costs by shielding homes from winter winds. The principle is simple but effective. By interrupting the wind's flow, you reduce its power. This is not fighting the wind, but understanding it, working with its nature to create more hospitable conditions. Every row of poplars or cedars standing against the horizon is a partnership between humans and the atmosphere. Wind energy and human-use windmills have harnessed wind energy for over 1,000 years. Humans have been capturing wind energy for centuries. The earliest windmills appeared in Persia over 1,000 years ago. Simple vertical axis devices used to grind grain and pump water. The technology spread westward, and by the medieval period, windmills dotted the landscapes of Europe. The iconic Dutch windmills, with their great wooden sails, drained polders and ground grain, enabling the Netherlands to reclaim land from the sea. Windmills became symbols of ingenuity, turning invisible air, currents, into mechanical power. In the American West, windmills pumped water for livestock and homesteads, their distinctive silhouettes marking remote ranches. These machines were reliable, requiring no fuel, operating whenever the wind blew. Though largely replaced by engines and electric pumps, many old windmills still stand, monuments to a time when wind was an essential partner in survival. Modern wind turbines generate electricity from kinetic energy. Today, wind energy is experiencing a renaissance. Modern wind turbines, far larger and more sophisticated than old windmills, convert wind's kinetic energy into electricity. As wind pushes against rotor blades, they spin, turning a generator. The amount of energy captured depends on wind speed, rotor size, and efficiency. A single large turbine can generate enough electricity to power hundreds of homes. Wind farms, clusters of turbines, can generate megawatts or even gigawatts of power. Offshore wind farms, built in shallow coastal waters, take advantage of strong, steady ocean winds. Wind energy is clean, producing no emissions, and renewable. As long as the sun heats Earth unevenly, wind will blow. It is not without challenges. Wind is variable, sometimes abundant, sometimes absent. Turbines require maintenance. Birds and bats can collide with blades. Yet, as technology improves and climate concerns grow, wind energy is expanding rapidly, reshaping how societies generate power. Wind farms are appearing across prairies, coasts, and offshore waters. Drive through certain parts of Texas, Iowa, or Kansas, and the horizon bristles with wind turbines. Their slender towers rise hundreds of feet, supporting three-bladed rotors that sweep gracefully through the air. Wind farms have become a defining feature of many rural landscapes. Offshore, turbines rise from the sea, their foundations anchored to the seabed or floating on deep water. These offshore installations can access stronger, more consistent winds. Europe leads in offshore wind development, with vast farms in the North Sea. In the United States, projects are expanding along the Atlantic coast. Each turbine is an engineering marvel, with blades longer than a football field and nacelles housing complex gearboxes and generators. Wind farms represent a shift in energy philosophy, from extracting and burning ancient carbon to harvesting the atmosphere's endless motion. Sailing vessels have crossed oceans powered purely by wind for millennia. Long before engines, wind was the only force that could propel ships across open ocean. Ancient Egyptians sailed the Nile with simple, square-rigged vessels. Polynesian navigators crossed the Pacific in outrigger canoes, reading winds and stars. Vikings reached North America in their longships. The age of sail saw clipper ships racing across oceans, their tall masts carrying acres of canvas. A skilled crew could coax speed from the slightest breeze, adjusting sails to capture wind from any direction. Sailors learned the moods of the wind, the steady trades, the dangerous doldrums where wind disappeared entirely, the roaring forties where westerlies blew fierce and cold. Though most commercial shipping now relies on engines, sailing has not vanished. Yachts still cross oceans, competitive sailors race in regattas, and a few cargo vessels are experimenting with modern sails to reduce fuel consumption. The romance of sail endures, that ancient partnership between human skill and moving air. Kites were among humanity's first attempts to ride the wind. For thousands of years, people have sent objects into the sky on strings, letting wind lift them. Kites likely originated in China over 2,000 years ago. They were used for signaling, measuring distances, testing wind, and simple enjoyment. Across Asia, kite flying became an art form, with elaborate designs and competitive festivals. Benjamin Franklin famously flew a kite in a thunderstorm, demonstrating that lightning was electrical. In the 19th century, researchers used large kites to lift weather instruments, and even people, conducting early experiments in aviation. The Wright brothers tested airfoil shapes with kites before building their airplane. Today, kiteboarding has become a popular sport, with riders harnessed to large kites that pull them across water at high speeds. Kites are simple, just fabric and string, yet they reveal something profound. Wind has lift, force, energy. It can carry things skyward. It can be harnessed, played with, understood. Every kite dancing in the breeze is a tiny experiment in aerodynamics. Hot air balloons drift wherever the wind carries them. Balloons are unique among aircraft. They have no engines, no control surfaces, no way to steer. They go where the wind takes them. A balloon rises by heating the air inside its envelope, making it less dense than the surrounding atmosphere. Once aloft, it drifts with the wind at whatever altitude the pilot chooses. By ascending or descending, pilots can find winds blowing in different directions, using this variation to navigate roughly toward a destination. But ultimately, the wind decides. Ballooning requires acceptance, a willingness to surrender, control, and trust the atmosphere. The experience is serene, no engine noise, just the occasional roar of the burner and the whisper of wind. Floating above the landscape, moving with the air, passengers feel connected to the wind in a way no other flight provides. It is a gentle reminder that not all travel is about control. Sometimes, the journey is about letting go and seeing where the wind carries you. Wind catchers and wind towers have cooled buildings in hot climates for centuries. In the deserts of the Middle East, ancient architects designed buildings to work with wind rather than against it. Wind catchers, tall towers with openings at the top, capture breezes and channel them down into interior rooms. As air descends, it cools the space and creates circulation. Some designs combined wind catchers with underground water channels. Air passing over the water cooled further before entering living areas. These passive cooling systems required no energy, just clever design and understanding of wind behavior. In hot, arid climates, they made life tolerable. Even today, modern architects study these traditional designs, seeking to reduce reliance on air conditioning. By orienting buildings correctly, positioning windows to catch breezes, and creating pathways for air to flow through, structures can be naturally ventilated. Wind, when understood and invited in, becomes a partner in comfort. It is an ancient technology, rediscovered in an age seeking sustainability. Wind in the atmosphere's layers. The troposphere is where weather and most winds occur. The atmosphere is layered, each zone with distinct characteristics. The lowest layer, the troposphere, extends from the surface to about 6 miles at the poles and 11 miles at, say, the equator. This is where we live, where clouds form, where weather happens. Almost all the atmosphere's water vapor resides here, and temperature decreases with altitude. Most winds we experience, from gentle breezes to hurricanes, occur in the troposphere. The jet stream flows near its upper boundary. Above the troposphere lies the stratosphere, where temperature begins increasing with height due to ozone absorbing solar radiation. Winds in the stratosphere are generally weaker and more uniform than below. The ozone layer resides here, protecting life from ultraviolet radiation. Higher still are the mesosphere, thermosphere, and exosphere, progressively thinner and more tenuous. But for wind as we know it, moving air that we feel and that shapes weather, the troposphere is home. The stratosphere is calmer, with steady winds at high altitudes. Above the weather, in the stratosphere, conditions are markedly different. The air is thin and dry. Clouds rarely form here, except for rare nacreous clouds near the poles and occasional overshooting thunderstorm tops. Winds are steadier, lacking the turbulence and variability of the troposphere. One notable feature is the stratospheric polar vortex, a large-scale circulation of strong winds encircling the poles during winter. When this vortex is strong and stable, cold air remains locked over the Arctic or Antarctic. When it weakens or becomes distorted, cold air can spill into lower latitudes, causing severe winter weather. Sudden stratospheric warming events, where temperatures in the stratosphere rise rapidly, can disrupt the polar vortex, influencing weather patterns for weeks. Commercial jets cruise in the lower stratosphere, enjoying smooth air and efficient flight. Here, wind is less a creator of weather and more a steady current, quietly circling the globe. Gravity waves ripple through the atmosphere like waves in water. The atmosphere, though invisible, behaves in some ways like a fluid, just as waves ripple. Across a pond, waves can propagate through air. Gravity waves, not to be confused with gravitational waves from astrophysics, are oscillations in the atmosphere driven by buoyancy. When air is displaced vertically, gravity pulls it back down, but it overshoots, creating an oscillation. These waves can be triggered by thunderstorms, mountains, or fronts. They travel horizontally and vertically, carrying energy through the atmosphere. Gravity waves can produce striking cloud patterns, regular ripples in altocumulus or cirrus, and they influence turbulence and mixing. In the upper atmosphere, gravity waves can grow large enough to break, like ocean waves on a beach, depositing energy and momentum. Though invisible and often unnoticed, gravity waves are a fundamental part of atmospheric dynamics, linking different layers and redistributing energy. The air above us is not still but filled with oscillations and currents we rarely perceive. Atmospheric tides are caused by the sun and moon, though much weaker than ocean tides. Just as the moon's gravity raises tides in the ocean, it also affects the atmosphere. Atmospheric tides are much smaller than ocean tides, but measurable. The moon's gravitational pull creates a slight bulge in the atmosphere, and as Earth rotates, this bulge appears to move. Additionally, solar heating creates thermal tides, regular oscillations in temperature and pressure that follow the sun's daily cycle. These tides influence surface pressure slightly, usually only a few millibars, but they are consistent and predictable. In the upper atmosphere, tides become more significant, driving winds and temperature variations. For most people, atmospheric tides are imperceptible, masked by the larger variability of weather. But they are there, subtle reminders that the atmosphere responds not only to heating and Earth's rotation, but also to the gravitational tugs of celestial bodies. Even the air we breathe feels the pull of the moon. Solar wind is a stream of particles from the sun, not atmospheric wind. Beyond Earth's atmosphere, space is not empty. The sun constantly emits a stream of charged particles, mostly electrons and protons, flowing outward at speeds exceeding 1 million miles per hour. This is the solar wind, though it is not wind in the atmospheric sense. It carries the sun's magnetic field into space, interacting with planets and other objects. When solar wind reaches Earth, it encounters our magnetic field. Most particles are deflected, but some funnel toward the poles, where they collide with atmospheric gases, creating auroras. Strong bursts of solar wind, caused by coronal mass ejections, can disrupt satellites, communication, and power grids. The solar wind also shapes the heliosphere, a bubble around the solar system where the sun's influence dominates. Beyond that lies interstellar space. Though not atmospheric wind, the solar wind reminds us that currents and flows exist at every scale, from the gentlest breeze on a hillside to particle streams racing between stars. Winds in extreme environments, polar winds, can be brutally cold and persistent. The polar regions experience some of Earth's harshest winds. Katabatic winds, driven by gravity, form when dense, cold air over ice sheets flows downslope toward the coast. In Antarctica, these winds can be relentless, blowing for days or weeks with speeds sometimes exceeding 100 miles per hour. They are cold, dry, and powerful, creating whiteout conditions even under clear skies by lifting surface snow. Explorers and researchers in Antarctica must contend with these winds, which can make temperatures feel far colder than the thermometer indicates. The wind chill factor, a measure of how cold wind makes exposed skin feel, becomes critical in polar environments. In the Arctic, winds are generally not as extreme as Antarctica, but can still be fierce, especially during winter storms. Blizzards combine snow and wind into blinding, dangerous conditions. In these extreme environments, wind is not a gentle presence, but a force that must be respected, prepared for, and sometimes simply endured. Hurricanes are the most powerful wind systems on Earth. Hurricanes, known as typhoons in the Pacific and cyclones in the Indian Ocean, are among nature's most formidable displays of wind. They form over warm tropical oceans where water temperatures exceed 80 degrees Fahrenheit. Warm, moist air rises, creating low pressure. More air rushes in, spiraling due to the Coriolis effect. As the system organizes, winds accelerate. In a mature hurricane, winds spiral inward, converging toward the eye, then rise violently in the eye wall, the ring of strongest winds. Hurricanes are classified by sustained wind speeds. A Category 5 hurricane, the highest designation, has winds exceeding 157 miles per hour. These storms can be hundreds of miles wide, persist for weeks, and release energy equivalent to multiple nuclear bombs every second. Storm surge, driven by wind pushing water ashore, is often the deadliest aspect. The wind itself can shred buildings, uproot trees, and turn debris into projectiles. Hurricanes are awe-inspiring and terrifying. Nature's most powerful winds gathered into swirling giants. The eye wall contains a hurricane's strongest winds and rain. At the heart of every strong hurricane lies the eye, a calm region of light winds, clearing skies, and even sunshine. Surrounding the eye is the eye wall, a towering ring of thunderstorms where the hurricane's strongest winds roar. In the eye wall, air spirals inward and upward at tremendous speeds. Updrafts can reach over 100 miles per hour. Rain falls in torrents. Lightning flashes. This is the most destructive part of the storm. As a hurricane passes over, locations experience the eye wall's fury twice, before and after the eye. The calm of the eye is deceptive, a brief respite before conditions worsen again. The eye wall can contract and expand during a phenomenon called an eye wall replacement cycle. A new outer eye wall forms, choking off the inner eye wall, and the storm's intensity may fluctuate. Flying into a hurricane, research aircraft penetrate the eye wall to reach the eye, gathering data in one of the most dangerous environments for aviation. The eye wall is where wind reveals its ultimate power. Hurricane-force winds extend far from the storm's center. While the eye wall holds peak winds, a hurricane's influence extends much farther. Hurricane-force winds, sustained winds of at least 74 miles per hour, can reach over 100 miles from the center in large storms. Tropical storm-force winds, 39 to 73 miles per hour, can extend even farther. This means a hurricane hundreds of miles offshore can still batter coastlines. Storm surge begins building far from landfall as winds push water toward shore. Rainfall from outer bands can cause flooding hundreds of miles away. Tornadoes, spawned by hurricanes' outer circulation, can strike far from the eye. After landfall, hurricanes weaken as they lose their warm water fuel, but they can retain dangerous winds for days as they move inland. The 2005 Hurricane Katrina devastated New Orleans, a city that was not even directly hit by the eye wall. The wind, rain, and surge affected a massive area, demonstrating that hurricanes are not pinpoint disasters, but regional catastrophes. Typhoons in the Pacific can be even larger than Atlantic hurricanes. The Western Pacific Ocean, the largest expanse of tropical water on Earth, breeds the most intense tropical cyclones. Typhoons here have more room to develop and often reach extraordinary sizes and strengths. Super Typhoon Tip in 1979 remains the largest and most intense tropical cyclone on record, with winds of 190 miles per hour and a diameter of over 1,300 miles, half the width of the continental United States. The warm waters, favorable atmospheric conditions of the Pacific allow storms to intensify rapidly. Typhoons regularly threaten the Philippines, Taiwan, Japan, and coastal China, bringing catastrophic winds, rain, and storm surge. The terminology differs by region, but the physics is the same. These are rotating systems powered by heat and moisture, organized by Earth's rotation, capable of unleashing winds that few structures can withstand. The Pacific's typhoons remind us that Earth's most powerful winds are not anomalies, but recurring features of a warm, watery planet. Tropical cyclones cannot form at the equator due to insufficient Coriolis effect. Despite their tropical nature, hurricanes have a peculiar limitation. They do not form within about 5 degrees of the equator. The Coriolis effect, which causes air to curve and creates the rotation necessary for cyclone formation, is 0 at the equator and too weak in the immediate vicinity. Without sufficient Coriolis force, winds cannot organize into a rotating system. They may converge and create thunderstorms, but they do not spin into hurricanes. This means regions directly on the equator, while often rainy and prone to storms, do not experience hurricanes. The storms form in the tropics, between roughly 5 and 20 degrees latitude, where the Coriolis effect is strong enough to initiate rotation, but where ocean temperatures are still warm. This geographical constraint is one of the many precise conditions required for hurricane formation. It is a reminder that wind, for all its power, is governed by physical laws, by invisible forces and boundaries written into the planet's geometry. Wind and living things. Seeds and spores travel vast distances on the wind. Plants, unable to move, have evolved remarkable strategies for dispersal, and many rely on wind. Dandelion seeds, each attached to a delicate parachute of silky hairs, drift on the slightest breeze, sometimes traveling miles before settling. Maple seeds spin like helicopters, slowing their descent and catching horizontal winds. Pine cones release winged seeds that flutter away. Tumbleweeds break free and roll across plains, scattering seeds as they go. Fungi release millions of microscopic spores that ride air currents, spreading across continents. Fern spores can remain aloft for days, carried by high-altitude winds. Even orchid seeds, among the tiniest in the plant kingdom, drift like dust. Wind dispersal allows plants to colonize new areas, escape competition, and maintain genetic diversity. After volcanic eruptions or glacial retreats, wind-carried seeds are often the first to arrive, beginning the slow process of succession. Every gust carries invisible passengers, the next generation of forests, meadows, and gardens, traveling toward uncertain destinations. Birds use wind for migration, soaring on thermals and tailwinds. For birds, wind is both challenge and resource. Migrating birds time their journeys to take advantage of favorable tailwinds. Tailwinds speed their travel, reducing the energy cost of flight. Headwinds ground them, forcing delays. Many species fly at night when winds are often calmer and more predictable. Large soaring birds, like hawks, eagles, and vultures, use thermals, rising columns of warm air created by surface heating. They circle within thermals, gaining altitude without flapping, then glide forward, descending slowly until they find the next thermal. This technique allows them to cover vast distances with minimal energy expenditure. Seabirds, like albatrosses, use a different strategy called dynamic soaring. They exploit wind gradients over the ocean, flying close to the waves where wind is slower, then climbing into faster wind above, extracting energy from the difference. These birds can travel thousands of miles without flapping. Wind for them is not an obstacle but a highway. Monarch butterflies ride winds during their incredible migrations. Among the most astonishing migrations is that of the monarch butterfly. Each fall, millions of monarchs from eastern North America travel up to 3,000 miles to overwintering sites in the mountains of central Mexico. No individual butterfly completes a full round trip. The journey spans multiple generations. These delicate insects, weighing less than a gram, navigate using the sun, an internal compass, and environmental cues. They also use wind strategically. Monarchs often wait for favorable winds before migrating and can be carried long distances by strong tailwinds. During migration, they have been observed at high altitudes, riding air currents. Some fly over the Gulf of Mexico, a journey requiring sustained flight over open water. The wind aids them, but it also poses risks. Strong storms can blow them off course or exhaust them. Despite their fragility, monarchs have perfected the art of using wind to accomplish one of nature's most remarkable journeys. Insects drift in the atmospheric boundary layer by the billions. While large animals use wind strategically, many small insects are at its mercy. Yet, this is not necessarily a disadvantage. Aphids, small flies, and other tiny insects are constantly being lofted into the air by wind. The atmospheric boundary layer, the lowest part of the atmosphere, churns with updrafts and downdrafts. Insects caught in these currents can be carried miles, sometimes hundreds of miles. This passive dispersal allows species to colonize new areas rapidly. Farmers have long known that insect pests can appear suddenly, blown in by wind. Locusts form swarms that migrate with wind systems, devastating crops across entire regions. Studies using specialized nets and radar have revealed that billions of insects are aloft at any given time, forming an invisible aerial plankton. They are moved by forces beyond their control. Yet this movement is part of their life strategy, a way to spread, to find new resources, to survive. Spiders balloon on silk threads, floating to new territories. Spiders, though not equipped with wings, have found a way to fly. Young spiders, and sometimes adults, climb to a high point, such as a fence post or blade of grass, release strands of silk, and wait. When the breeze catches the silk, the spider lets go and is carried aloft. This behavior, called ballooning, allows spiders to travel remarkable distances. Some have been found on ships far from land, and they are often among the first colonizers of new volcanic islands. Ballooning spiders have been collected by aircraft at altitudes of thousands of feet. The silk strands catch the wind like tiny sails or parachutes. Once aloft, the spider is at the mercy of air currents, landing wherever the wind takes it. This may seem random, but it is effective. By dispersing widely, spiders increase their chances of finding suitable habitat and avoid overcrowding. On a sunny autumn day, fields can shimmer with thousands of silk strands, evidence of countless spiders embarking on wind-borne journeys. Pollen grains cause allergies, as wind carries them through the air. For many plants, especially grasses, trees, and weeds, wind is the primary pollinator. These plants produce enormous quantities of pollen, lightweight, and designed to drift on air currents. A single ragweed plant can release millions of pollen grains in a day. Wind carries pollen from flower to flower, enabling fertilization without the need for insect pollinators. For humans, this creates a seasonal challenge. Airborne pollen triggers allergic reactions in millions of people. Spring tree pollen, summer grass pollen, and fall weed pollen create overlapping waves of misery for allergy sufferers. Pollen grains are so small that they can travel hundreds of miles. Ragweed pollen from the Midwest has been detected far out over the Atlantic. On dry, windy days, pollen counts soar. Rain cleanses the air temporarily, but wind quickly resupplies it. For plants, wind pollination is efficient, requiring no colorful flowers or nectar. For humans, it is a reminder that we share the air with countless invisible particles carried by wind in their ancient reproductive journeys. Wildfires spread rapidly when driven by strong winds. Wind and fire are a dangerous combination. A wildfire burning in calm conditions moves relatively slowly, allowing firefighters time to establish containment lines. But when wind picks up, everything changes. Wind supplies fresh oxygen, intensifying combustion. It bends flames forward, preheating and igniting vegetation ahead of the fire. Embers, lifted by wind, can be carried miles, starting new spot fires beyond containment lines. In extreme cases, wind-driven wildfires move faster than people can run, racing across landscapes, jumping roads and rivers. The 2018 Camp Fire in California, driven by strong winds, spread with terrifying speed, destroying the town of Paradise and killing 85 people. Firefighters speak of red flag warnings, conditions of low humidity, dry vegetation, and high winds that create extreme fire danger. In such conditions, fires can become uncontrollable, defying suppression efforts. Wind-driven wildfires have always been part of nature, shaping ecosystems. But as human development pushes into fire-prone areas, wind's role in spreading fire becomes ever more consequential. Dust storms can transport soil and pathogens across continents. Wind does not only carry seeds and pollen, it also moves dust, sometimes in staggering quantities. Dust storms form when strong winds blow over dry, loose soil. The finest particles, silt and clay, can be lifted high into the atmosphere and carried thousands of miles. Dust from the Sahara Desert regularly crosses the Atlantic, reaching the Caribbean and even the Amazon rainforest, where it deposits nutrients. This transcontinental transport has ecological significance. Saharan dust supplies minerals like phosphorus to Amazon soils, which are otherwise nutrient-poor. However, dust can also carry harmful materials. Fungal spores, bacteria, and pollutants travel with dust. Dust events have been linked to respiratory illnesses, coral disease, and reduced air quality far from the source. In the 1,930 seconds, the Dust Bowl saw massive dust storms engulf the American Great Plains, darkening skies as far as the East Coast. These storms resulted from drought and poor farming practices that left soil exposed. Wind, encountering this vulnerability, stripped away topsoil, carrying it eastward in choking clouds. Legendary and unusual winds. Chinook winds, warm and dry regions downslope from mountains. In the shadow of the Rocky Mountains, residents of the Great Plains occasionally experience a dramatic weather phenomenon. The Chinook wind, named after the Chinook people of the Pacific Northwest, is a warm, dry wind that descends the eastern slopes of the Rockies. It forms when moist air from the Pacific ascends the western slopes, cooling and releasing precipitation. As the now dry air descends the eastern side. It compresses and warms at a rate of about 10 degrees Celsius per 1,000 meters. By the time it reaches the plains, it can be much warmer than the air it replaces. Chinooks can raise temperatures by 20, 30, even 40 degrees Fahrenheit in a few hours, melting snow and bringing midwinter thaws. These winds are powerful, sometimes gusting over 100 miles per hour. They can damage structures, ground aircraft, and create hazardous driving conditions. Yet, they are also welcomed, providing relief from bitter cold and shortening winter's grip. Foehn winds in the Alps produce similar warming effects. The Chinook is not unique. Similar winds occur wherever moist air crosses mountain ranges. In the Alps, they are called Foehn winds. In Southern California, the Santa Ana winds. In the Andes, the Zonda. The mechanics are the same. Air forced upward cools and loses moisture. Descending the opposite side, it warms and dries. Foehn winds in. The Alps have been observed since ancient times. They are associated with clear skies, low humidity, and sometimes unsettling psychological effects. Some people report headaches, irritability, and sleeplessness during Foehn events. Though the reasons are debated, these winds also increase wildfire risk. Dry vegetation, low humidity, and strong winds create dangerous conditions. In Austria and Switzerland, Foehn-related fires have historically caused significant damage. Yet, Foehn winds also bring benefits, melting snow, extending growing seasons, and creating spectacular cloud formations, including the famous Foehn Wall, a band of clouds marking where moist air condenses before descending. Santa Ana winds fuel California's most destructive wildfires. Southern California's Santa Ana winds are infamous. They form when high pressure builds over the Great Basin, the arid region between the Rockies and the Sierra Nevada. Air flows outward from this high, accelerating as it funnels through mountain passes and canyons toward the coast. As it descends, it warms and dries. Santa Anas typically occur in fall and winter, bringing hot, dry conditions when vegetation is already parched from summer. Humidity can drop below 10%. Winds gust over 50 miles per hour, sometimes exceeding 100. Under these conditions, any spark can ignite an inferno. Many of California's worst wildfires, including the 1991 Oakland Hills fire and the 2018 Woolsey fire, were driven by Santa Ana winds. Firefighting becomes nearly impossible. Flames leap ahead, embers fly miles, and firestorms generate their own winds. The Santa Anas have been part of California's climate for millennia, but as urban areas expand into wildlands, their danger intensifies. The Mistral funnels cold air toward the Mediterranean coast. In southeastern France, the Mistral wind is a dominant feature of life. It blows from the north, funneling cold air from central France through the Rhône Valley toward the Mediterranean coast. The Mistral is strong, often sustained at 30 to 40 miles per hour, with gusts much higher. It can persist for days. The name comes from the Provençal word for masterly, reflecting its dominance. The Mistral brings clear skies, low humidity, and cooler temperatures. While it moderates summer heat, it can make winter uncomfortably cold. Architecture in Provence reflects the Mistral's influence. Buildings are oriented away from the north, and cypresses are planted as windbreaks. The wind also affects agriculture. It can damage crops, but also dries grapes on the vine, concentrating sugars and contributing to the character of regional wines. Sailors on the Mediterranean respect the Mistral, which can whip the sea into dangerous conditions. For centuries, this wind has shaped the landscape, culture, and economy of southern France. Haboobs are massive dust storms that tower like walls across deserts. In arid regions, a dramatic sight occasionally appears on the horizon. A towering wall of dust, thousands of feet high and miles wide, advances with startling speed. This is a haboob, an intense dust storm driven by the outflow from collapsing thunderstorms. As rain falls into dry air, it evaporates, cooling the air and making it dense. This cold air plummets to the ground and rushes outward as a powerful gust front. As it races across dry, loose soil, it lifts enormous quantities of dust. Visibility drops to zero. Winds can reach 60 miles per hour. Haboobs are common in the Sahara, where the name originates from the Arabic word for blasting or drifting. They also occur in the American Southwest, particularly in Arizona. Phoenix has experienced haboobs that engulf the entire metropolitan area, halting traffic and causing respiratory hazards. These dust storms are spectacular and dangerous, a reminder of wind's power to reshape the visible world in moments. Willy Willies are Australian dust devils and small whirlwinds. In the outback of Australia, small whirlwinds commonly form on hot days. Locally called Willy Willies, they are similar to dust devils found in deserts worldwide. They spin across red earth, lifting dust into slender columns that twist and sway. Most are harmless, dissipating after a few minutes. Occasionally, stronger Willy Willies can startle livestock or scatter debris. Aboriginal Australians incorporated Willy Willies into their stories and art, seeing them as spirits or manifestations of ancestral beings. The term Willy Willy is thought to derive from an Aboriginal word. These whirlwinds, though small, are part of the atmosphere's endless repertoire of motion. They are reminders that wind does not only blow in straight lines, but can organize into spirals and vortices at many scales, from dust devils that barely reach above your head to tornadoes that tower into thunderstorms. Nor'easters batter the eastern United States with powerful winds and waves. Along the east coast of the United States, particularly in winter, powerful storms called nor'easters develop. The name comes from the strong northeasterly winds that blow ahead of the storm. Nor'easters form when a low-pressure system moves up the coast, drawing in cold air from the north and warm, moist air from the Atlantic. The collision fuels intense storms that can bring heavy snow, rain, coastal flooding, and damaging winds. Nor'easters can stall offshore, battering the coast for days. The 1991 Halloween nor'easter, immortalized in the book and film The Perfect Storm, combined with a hurricane, creating a meteorological monster. The blizzard of 1888 buried the Northeast in snow, paralyzing cities. Nor'easters shape the region's climate and history. They carve coastlines, sink ships, and test the resilience of communities. The howling northeast wind, cold and relentless, is one of winter's harshest expressions along the Atlantic seaboard. Katabatic winds in Antarctica are the coldest, fiercest winds on Earth. Antarctica is a continent of extremes, and its winds are no exception. Katabatic winds, driven by gravity pulling dense, cold air down from the high interior ice sheet, can be ferocious. Commonwealth Bay in East Antarctica holds the record for the highest average wind speed on Earth, with annual averages exceeding 50 miles per hour and frequent gusts over 100. These winds blow almost constantly, driven by the extreme cold of the polar plateau. The air over the ice sheet cools to temperatures far below zero, becomes incredibly dense, and slides downslope with accelerating force. The wind is dry, scouring, capable of sandblasting exposed surfaces with ice crystals. Explorers describe the sound as a roar, the force as a physical assault. Tents must be anchored with extraordinary care. Frostbite risk is severe, yet These winds are also part of what makes Antarctica unique. They transport cold air to the coast, influence ocean circulation, and create some of the planet's most inhospitable and strangely beautiful conditions. Wind in mythology and culture. Aeolus was the Greek god of winds, keeper of the storm winds. In ancient Greek mythology, winds were not impersonal forces but divine beings. Aeolus, appointed by Zeus, was the keeper of the winds. He lived on the floating island of Aeolia, where he kept the storm winds imprisoned in a cave or in bags, releasing them only when commanded by the gods. In Homer's Odyssey, Aeolus gives Odysseus a bag containing all the adverse winds, allowing him to sail home safely. But Odysseus's crew, thinking the bag contains treasure, opens it. The winds escape, driving the ships back and prolonging their journey. This myth reflects ancient people's understanding of wind as powerful, capricious, and subject to forces beyond human control. The Greeks also personified the four directional winds: Boreas, the cold north wind; Notus, the wet south wind; Zephyrus, the gentle west wind; and Eurus, the east wind. Each had a personality and mythology, weaving wind into the stories that explained the world. Native American traditions often personified winds as spirits or beings. Indigenous peoples across North America developed rich traditions involving wind. Many tribes personified the four winds, each associated with a direction, season, and qualities. The north wind might be cold and fierce, bringing winter. The south wind warm and nurturing, bringing summer. The west and east winds had their own characters. These were not mere metaphors, but spiritual beings with agency. Stories tell of wind as a trickster, a helper, or a force to be respected. The Navajo Dine Bahanet, or creation story, describes wind as one of the holy people, essential to life. Wind is said to enter each person at birth, giving life and thought. Breath and wind are connected, both called Nilchi. This intimate relationship between wind and life, common across many indigenous traditions, reflects a deep observation of nature. Wind is not just weather, it is spirit, breath, and the movement of life itself. Sailors have always respected and feared the wind's power. For those whose lives depend on the sea, wind is everything. Too little, and ships sit becalmed, drifting aimlessly. Too much, and they are driven onto rocks, capsized, or torn apart. Sailors developed deep knowledge of winds, learning to read the sky, the waves, and the feel of the air. They created names and lore. The doldrums, the windless equatorial regions where ships could sit motionless for weeks. The roaring 40s, 50s, and 60s, southern latitudes where westerly winds howl relentlessly. The horse latitudes, subtropical regions of high pressure and light winds, supposedly named because ships carrying horses sometimes had to throw them overboard when becalmed and running low on water. Superstitions arose. Whistling aboard ship was believed to summon wind, sometimes welcome, sometimes not. Sailors spoke of wind as having moods, temperaments. Respect for the wind was not romantic, but practical. It could grant passage or deal death. Even today, with engines and weather forecasts, sailors maintain this respect. Wind instruments and chimes have made wind audible for millennia. Humans have long sought to capture wind's voice. Wind chimes, originating in ancient Asia, hang pieces of metal, wood, or bamboo that strike each other when moved by wind. The sounds are random yet harmonious, a conversation between breeze and material. Wind chimes served decorative, spiritual, and practical purposes. Some believed they warded off evil spirits. Farmers used them to scare birds. Temples hung elaborate chimes that sang with the wind. Wind instruments, flutes, panpipes and horns also connect breath and wind to music. Playing a flute is directing your breath, your personal wind, through a carefully designed channel. The Aeolian harp, named after Aeolus, is a stringed instrument played entirely by wind. Placed in a window or outdoors, the wind vibrates its strings, creating ethereal, ever-changing tones. These instruments and devices allow us to hear what is usually silent, giving voice to the invisible currents flowing around us. Flags and banners reveal wind direction and strength at a glance. Before anemometers and weather stations, people relied on simple indicators to understand wind. Flags have served this purpose for centuries. A flag's position and movement immediately convey wind direction and approximate strength. Limp means calm. Fluttering means light breeze. Fully extended and snapping means strong wind. Mariners read flags to gauge conditions. Airports use windsocks, conical fabric tubes that align with the wind and inflate based on speed. Windsocks are calibrated, their droop or extension indicating specific wind velocities. Even today, with sophisticated instruments, these visual indicators remain invaluable. They are simple, reliable, and require no power. Watching a flag ripple in the breeze connects us to a long tradition of reading the wind, of understanding from visible motion what the invisible air is doing. It is a reminder that knowledge does not always require complexity. Sometimes, a piece of cloth tells you everything you need to know. Windmills became symbols of regions that harnessed wind's power. Certain landscapes are inseparable from their windmills. The Netherlands, with its hundreds of historic windmills, used them to drain polders, reclaiming land from the sea. These wooden giants, with their slowly turning sails, became national symbols. Don Quixote's futile charge against windmills in Cervantes's novel immortalized them in literature, representing both human ingenuity and folly. In La Mancha, Spain, rows of whitewashed windmills stand on hilltops, enduring icons. On Crete and the Greek islands, windmills ground grain and pumped water, their white towers dotting ridges. In the American Midwest, steel windmills pumped water for cattle, enabling settlement of arid regions. Each windmill is a testament to adaptation, a recognition that where wind blows consistently, it can be a partner. These structures, whether historic relics or functioning machines, are monuments to humanity's long relationship with moving air. The Beaufort scale classifies wind speeds by observable effects. In 1805, British Admiral Sir Francis Beaufort developed a system to standardize descriptions of wind at sea. The Beaufort scale classifies wind from 0 to 12, from calm to hurricane force, based on observable effects rather than precise measurements. Force 0 means smoke rises vertically, the sea like a mirror. Force 3 shows large wavelets, scattered whitecaps, and leaves and twigs in constant motion. Force 7 is a near gale, with whole trees swaying and difficulty walking against the wind. Force 12, hurricane force, brings devastation. The beauty of the Beaufort scale is its accessibility. Anyone can estimate wind strength by looking at flags, trees, waves, or the feel of the wind. Though anemometers now provide exact measurements, the Beaufort scale remains in use, particularly in maritime contexts. It bridges subjective experience and objective measurement, acknowledging that wind is understood not just through numbers, but through its tangible effects on the world. Wind and climate trade winds drive ocean currents and influence global climate. Wind does not only move air, it also moves water. The trade winds, blowing persistently across tropical oceans, push surface water westward. This creates ocean currents, like the north and south equatorial currents. As water accumulates on the western sides of ocean basins, it flows poleward, forming currents like the Gulf Stream and Kuroshio Current. These currents transport enormous quantities of heat from the tropics toward the poles, moderating climate. The Gulf Stream warms Western Europe, making it far milder than corresponding latitudes in North America. El Niño events occur when trade winds weaken, allowing warm water to slosh back eastward across the Pacific, disrupting weather patterns globally. Wind and ocean are coupled systems. Changes in wind patterns alter currents, which in turn affect wind by changing sea surface temperatures. Understanding wind is essential to understanding climate, for wind is one of the great movers of heat and moisture around the planet. The Hadley cell is a major atmospheric circulation driven by equatorial heating. The atmosphere's circulation can be thought of as several large loops or cells. The most prominent is the Hadley cell, named after George Hadley, who proposed it in 1735. Warm, moist air rises near the equator, driven by intense solar heating. This rising air creates the intertropical convergence zone, a band of clouds and thunderstorms. As the air rises, it cools and loses moisture, then flows poleward at high altitude. Around 30 degrees latitude, it descends, creating the subtropical, high-pressure belts, regions of clear skies and deserts like the Sahara and Arabian deserts. From there, air flows back toward the equator as the trade winds, completing the loop. The Hadley cell transports heat from the equator toward higher latitudes and drives the trade winds, the subtropical deserts, and tropical rainforests. It is a fundamental pattern of atmospheric motion, one of the engines of global wind and weather. Polar cells and feral cells complete the global circulation pattern. Poleward of the Hadley cells, the atmosphere organizes into additional circulation loops. The feral cells, lying between 30 and 60 degrees latitude, are driven indirectly by the Hadley and polar cells. Air flows poleward near the surface as part of the westerlies, then rises around 60 degrees and returns equatorward at altitude. The polar cells, over the Arctic and Antarctic, involve cold, dense air, sinking at the poles and flowing equatorward near the surface as polar easterlies, then rising around 60 degrees. These three-cell models, in each hemisphere, simplify a complex reality, but they capture the essential patterns. Together, these cells create the global wind belts, the trade winds, westerlies, and polar easterlies that encircle the planet. They are the atmospheric machinery redistributing solar energy, maintaining temperature gradients, and shaping the climate zones we experience, from tropical heat to polar cold. El Niño and La Niña involve shifts in Pacific trade winds. Every few years, the tropical Pacific undergoes a dramatic shift. Normally, trade winds blow westward, piling warm water in the western Pacific and allowing cold, deep water to upwell in the east. But during an El Niño event, the trade winds weaken or even reverse. Warm water spreads eastward across the Pacific. The upwelling weakens. This shift affects weather worldwide. Peru and Ecuador experience heavy rains. Indonesia and Australia face drought. The jet stream shifts, altering storm tracks across North America. Fisheries collapse as nutrient-rich cold water disappears. La Niña is the opposite phase. Trade winds strengthen, enhancing upwelling and cooling the eastern Pacific. This also has global consequences, often opposite to El Niño. These oscillations, known as the El Niño Southern Oscillation or ENSO, demonstrate how changes in wind patterns in one region can cascade through the climate system, affecting weather, ecosystems, and human societies worldwide. Climate change may alter wind patterns in coming decades. As Earth's climate warms due to increasing greenhouse gases, wind patterns are also changing. Models suggest that the Hadley cells may expand, pushing subtropical deserts poleward. The jet streams may shift or weaken, altering storm tracks and weather patterns. Some regions may become windier, others calmer. There is evidence that wind speeds over land decreased slightly in recent decades, a phenomenon called global stilling, though the causes are debated and trends vary by region. Offshore, winds may intensify in some areas, offering opportunities for wind energy, but also posing challenges. Changes in wind affect everything: agriculture, water resources, energy generation, and ecosystems. Understanding how wind will change as climate warms is a frontier of climate science. Wind, always dynamic, is now part of a planet-scale experiment, responding to forces humanity has unleashed, with consequences we are only beginning to understand. Windstorms and hurricanes may intensify in a warming climate. One of the concerns about climate change is whether storms will become more severe. Warmer sea surface temperatures provide more energy for hurricanes, potentially making the strongest storms more intense. While the total number of hurricanes may not increase, the proportion of major hurricanes, Category 4 and 5, may rise. Warmer air also holds more moisture, leading to heavier rainfall. Hurricane Harvey, in 2017, dumped unprecedented rain on Houston, an event made more severe by warm Gulf waters. Models suggest hurricanes may intensify more rapidly in the future, giving less warning time. Mid-latitude storms may also change, potentially intensifying in some regions. Wind, as a force driven by temperature differences and energy imbalances, responds to a warming world. Predicting exactly how is complex, but the potential for more extreme wind events is a serious consideration for planning and adaptation. The science of measuring wind anemometers measure wind speed using rotating cups or ultrasonic sensors. To understand wind quantitatively, we must measure it. The most common instrument is the anemometer. The classic design uses 3 or 4 cups mounted on horizontal arms that spin around a vertical axis. Wind catches the cups, causing rotation. The speed of rotation correlates with wind speed. Electronic sensors convert this rotation into a measurement. Cup anemometers are simple, reliable, and widely used. Another type, the ultrasonic anemometer, has no moving parts. It measures the time sound waves take to travel between transducers. Wind affects this travel time, allowing calculation of wind speed and direction. Ultrasonic anemometers can measure rapid fluctuations, making them valuable for research. Hot wire anemometers use a heated wire. Wind cools the wire, and the cooling rate indicates wind speed. Different instruments suit different applications, but all attempt the same thing: to quantify the motion of air, turning the invisible and intangible into numbers we can analyze. Weather vanes show wind direction and have ancient origins. Knowing wind speed is important, but so is direction. The weather vane, or wind vane, is one of the oldest meteorological instruments. A pointer, often shaped like an arrow or a rooster, is mounted on a vertical axis so it can rotate freely. The tail of the pointer catches the wind, causing the pointer to align with the wind direction. The opposite end indicates where the wind is coming from. Weather vanes have adorned buildings for millennia. The Tower of the Winds in Athens, built in the 1st century BCE, featured a bronze weather vane. Medieval churches often topped their steeples with rooster vanes, symbolizing vigilance. The tradition continues, with weather vanes serving both functional and decorative roles. Though modern sensors provide precise direction measurements, the weather vane endures. A simple, elegant device that needs no power and speaks a universal language, the direction of the wind. Doppler radar detects wind patterns inside storms and tornadoes. Advances in radar technology revolutionized meteorology. Doppler radar, used by weather services worldwide, not only detects precipitation but also measures the motion of raindrops and debris. By analyzing the frequency shift of reflected radar waves, meteorologists can determine whether rain is moving toward or away from the radar. This reveals wind patterns inside storms. Rotation within a thunderstorm, a precursor to tornadoes, appears as a couplet of inbound and outbound motion. Doppler radar allows forecasters to issue tornado warnings with greater lead time, saving lives. It also maps wind shear, downbursts, and gust fronts. Dual polarization radar adds another dimension, measuring the shape and size of precipitation particles, distinguishing rain from hail or debris. When a tornado is on the ground, radar can detect the debris ball, a signature of strong winds lofting objects. Doppler radar turns the invisible winds aloft into colorful, interpretable images, giving us eyes into the storm. Radiosonde balloons carry instruments to measure upper atmosphere winds. While surface winds are relatively easy to measure, winds aloft require different methods. Twice daily, weather services around the world release weather balloons, also called radiosondes. These balloons carry instruments that measure temperature, humidity, and pressure as they ascend. GPS or radio tracking reveals the balloon's position, and by calculating its drift, meteorologists determine wind speed and direction at various altitudes. Radiosondes can reach heights of over 100,000 feet, well into the stratosphere, before the balloon bursts. The data they collect are crucial for weather forecasting, providing a vertical profile of the atmosphere. This information feeds into computer models, helping predict storms, fronts, and wind patterns. Despite the availability of satellites, radiosondes remain indispensable, offering precise measurements where satellites cannot. Each balloon's journey is a direct sampling of the wind, a voyage into the sky to bring back knowledge. Satellites observe global wind patterns from space. From orbit, satellites provide a view impossible from the ground, the entire planet's winds, continuously. Early weather satellites imaged clouds, allowing meteorologists to infer wind by tracking cloud motion over time. Modern satellites use more direct methods. Scatterometers measure wind speed and direction over the ocean by analyzing the roughness of the sea surface, which depends on wind. The radar signal scatters differently on calm versus choppy water. These instruments provide wind data over vast oceanic areas where few ships or buoys exist. Other satellites use LiDAR, laser beams that detect the motion of particles in the atmosphere, revealing wind profiles. Geostationary satellites, hovering over the equator, watch the same region continuously, tracking storms as they develop. Polar orbiting satellites scan the entire globe, piece by piece. Together, satellite observations have transformed meteorology, providing data that was once unimaginable, revealing the wind's global patterns in stunning detail. LiDAR and SODAR use light and sound to profile wind remotely. Beyond satellites, ground-based remote sensing instruments measure wind without physical contact. LiDAR, or light detection and ranging, emits laser pulses into the atmosphere. Particles in the air, dust, and aerosols scatter the light back. By measuring the Doppler shift of the returned light, LiDAR determines the motion of those particles, revealing wind speed and direction at various altitudes. Wind LiDAR has become a valuable tool at airports, detecting wind shear and turbulence. SODAR, or sonic detection and ranging, uses sound waves instead of light. It emits acoustic pulses and listens for echoes from temperature and turbulence variations in the air. The frequency shift of the echoes reveals wind. SODAR works well in the lower atmosphere, up to a few hundred meters. These technologies allow continuous, high-resolution wind measurements without launching balloons or aircraft, filling gaps in observational networks and improving forecasts. Wind tunnels let engineers study wind effects on structures and vehicles. Understanding wind is not only about measuring it in nature, but also about recreating it. Wind tunnels are enclosed spaces where air is blown at controlled speeds past models or objects. Engineers use them to study aerodynamics, testing airplane wings, car shapes, and building designs. By observing how wind flows around a model, introducing smoke or lasers to visualize airflow, they can identify turbulence, drag, and lift. Wind tunnels range from small desktop versions to massive facilities capable of testing full-scale aircraft. The Wright brothers built a crude wind tunnel to test airfoils before their first flight. Today, wind tunnels remain essential, despite computer simulations, because they provide real-world validation. Skyscrapers are tested to ensure they can withstand hurricane winds. Bridges are checked for wind-induced vibrations that could cause collapse, as happened with the Tacoma Narrows Bridge in 1940. Wind tunnels are where theory meets reality, where the invisible is made tangible and measurable. Wind's role in history. Wind-powered, navigation enabled the age of exploration. Before steam engines, ships were entirely at the mercy of wind. The ability to harness wind determined which voyages were possible and how long they took. Early explorers mapped wind patterns with their lives. Portuguese navigators, seeking routes to Asia, ventured down the African coast, learning the winds. They discovered the Volta do Mar, the turn of the sea, a clockwise route using the trade winds and westerlies to travel to and from Africa. This knowledge enabled the European age of exploration. Columbus crossed the Atlantic by sailing south to catch the trades, then returning north to catch the westerlies. Magellan's crew circumnavigated the globe, using winds to traverse the Pacific. These journeys were slow, dangerous, and dependent on wind. A favorable wind meant survival. Calm meant starvation. Storms meant death. The winds shaped exploration, determining which parts of the world were contacted first and how cultures interacted. The wind, in a very real sense, shaped history. The Dust Bowl reshaped American agriculture and migration. In the 1,930 seconds, a combination of drought and poor farming practices led to one of the worst environmental disasters in American history. The Great Plains, plowed extensively for wheat farming, lost its native grasses. When drought struck, the exposed topsoil dried out. Wind, encountering no resistance, lifted the soil into enormous dust storms. Black blizzards darkened the sky, burying homes, suffocating livestock, and forcing thousands to abandon their land. The Dust Bowl drove mass migration, with families fleeing to California in search of work, a journey immortalized in Steinbeck's The Grapes of Wrath. The disaster prompted changes in agricultural practices. The government promoted soil conservation, contour plowing, windbreaks, and crop rotation. The Dust Bowl remains a stark lesson in how land use and wind interact, and how ignoring natural systems can lead to catastrophe. It showed that wind, when given the opportunity, can strip away the very foundation of agriculture. Wind-borne diseases have spread through history, shaping epidemics. Wind carries more than seeds and dust. It also carries pathogens. Throughout history, the spread of diseases has sometimes been facilitated by wind. During the Great Plague of London, people believed that disease spread through miasmas, bad air, carried by wind. While the actual cause was fleas on rats, the association between wind and sickness persisted. More recently, scientists have confirmed that wind can transport viruses, bacteria, and fungal spores. Foot and mouth disease, affecting livestock, has spread between farms via airborne transmission over miles. Influenza viruses can survive in aerosols, potentially carried by wind. Fungal spores, causing crop diseases, travel continents on high-altitude winds. Valley fever, a disease caused by inhaling fungal spores from soil. Spikes after windstorms in the American Southwest. Wind's role in disease spread is complex and context-dependent, but it is real. Understanding this helps public health efforts, informing quarantine measures and disease monitoring. Sailors depended on winds, leading to rich maritime traditions. Life at sea shaped entire cultures, and wind was central to that life. Sailors developed intricate knowledge, passed through generations. They learned to read clouds, swell patterns, and the flight of birds to predict wind changes. Songs and shanties helped coordinate work and pass time during long voyages. The language of sailing is full of wind terms: leeward, windward, running before the wind, beating into the wind. Superstitions arose. A sailor might never whistle aboard ship for fear of summoning a gale, unless becalmed and desperate for wind. Red sky at night meant fair weather. Red sky in the morning, a warning. These traditions, born from intimate dependence on wind, gave sailors a sense of control and connection to forces beyond their power. Even today, with engines and GPS, sailors retain a respect for wind, understanding that on the ocean, it remains the ultimate authority. Wind direction influenced military tactics and outcomes of battles. Commanders have long understood that wind can be an ally or an enemy. Archers positioned themselves upwind to gain range. Arrows shot downwind fly farther. Smoke and dust from battles carried by wind could obscure vision, providing cover or confusion. Naval battles depended on wind. Gaining the weather gauge, being upwind of the enemy, allowed a fleet to control engagement, bearing down at will. The defeat of the Spanish Armada in 1588 was partly due to storms and unfavorable winds scattering the fleet. In World War I, poison gas attacks depended on wind direction. Gas drifted toward enemy trenches if the wind cooperated, but wind shifts could send it back, killing the attackers. In modern warfare, wind affects aerial operations, artillery accuracy, and the Machand spread of smoke or contaminants. Understanding wind remains a tactical consideration. Nature does not take sides, but wind can tilt the balance, rewarding those who understand and anticipate it. Wind and the future wind energy is among the fastest growing renewable energy sources. As the world seeks to reduce carbon emissions and combat climate change, wind energy is experiencing explosive growth. In 2020, global wind capacity exceeded 700 gigawatts, enough to power hundreds of millions of homes. Countries like Denmark generate over half their electricity from wind. China, the United States, and Germany lead in total capacity. Costs have dropped dramatically as technology improves and turbines grow larger. Offshore wind, once prohibitively expensive, is becoming competitive. Floating turbines are being developed for deep waters, opening vast new areas. Wind energy's advantages are clear. It is clean, renewable, and increasingly affordable. Challenges remain, including variability, grid integration, and environmental concerns. But momentum is strong. Wind energy represents a return to an ancient power source, reimagined with modern technology, harnessing the atmosphere's endless motion to power a sustainable future. Innovations in turbine design promise greater efficiency and lower costs. Wind turbine technology has advanced rapidly. Early turbines were small, inefficient, and loud. Modern turbines are engineering marvels. Blades exceed 300 feet long, sweeping areas larger than a football field. Taller towers reach higher, accessing stronger, steadier winds. Advanced materials, like carbon fiber, make blades lighter and stronger. Gearless direct drive generators reduce maintenance. Smart controls adjust blade pitch and rotor speed in real time, maximizing energy capture while protecting the turbine during high winds. Researchers are exploring bladeless turbines that oscillate rather than rotate, potentially quieter and safer for birds. Airborne wind energy systems use kites or drones tethered to the ground, reaching altitudes with stronger winds. These innovations aim to make wind energy more efficient, reliable, and acceptable. Each advance brings us closer to a future where wind, the ancient invisible force, powers modern civilization. Forecasting wind accurately is crucial for energy grids and safety. As wind energy expands, predicting wind becomes economically critical. Grid operators need to know how much wind power will be available hours or days ahead to balance supply and demand. Forecasters use numerical weather models, fed by observations from satellites, radio sondes, and surface stations. These models simulate atmospheric physics, predicting wind speed, direction, and variability. Machine learning is improving forecasts, identifying patterns in data. For wind farms, accurate forecasts mean better integration with the grid, reducing reliance on backup power. For public safety, forecasting severe winds, hurricanes, and tornadoes saves lives. Improvements in computing power and observational networks are steadily enhancing forecast accuracy. Yet, wind remains inherently variable, chaotic in detail. Perfect prediction is impossible, but each improvement helps society harness and prepare for wind more effectively. Wind research continues to uncover new atmospheric phenomena. Despite centuries of study, wind still holds mysteries. Researchers discover new phenomena regularly. Atmospheric rivers, narrow corridors of intense moisture transport in the atmosphere, deliver heavy precipitation to coasts, but are driven fundamentally by wind patterns. They were only widely recognized in the 1,990 seconds. Gravity waves in the atmosphere, mentioned earlier, are still being understood in detail. The interaction between wind and ocean, particularly how winds near the surface transfer energy to waves, remains an active research area. Scientists study wind on other planets, comparing Earth's patterns to those on Mars, Jupiter, or Titan, gaining insights into fundamental atmospheric physics. High-altitude winds in the mesosphere and thermosphere, regions difficult to access, are subjects of ongoing investigation. Every new discovery reminds us that the atmosphere is complex, that wind, though familiar, is still not fully understood. It invites curiosity and continued exploration. Understanding wind helps us adapt to a changing climate. Wind is both a driver and a responder in the climate system. As climate changes, wind patterns shift, affecting agriculture, water resources, energy, and hazards. By studying wind, we can anticipate these changes and adapt. Farmers may alter crop choices based on changing wind patterns and moisture delivery. Cities can design buildings to withstand projected future wind extremes. Energy planners can site wind farms where resources will be abundant decades from now. Understanding wind's role in spreading wildfires, diseases, and pollutants informs risk management. Wind connects distant places, carrying consequences across borders. Climate change is a global challenge, requiring global understanding, and wind, ever in motion, is a key thread connecting it all. The more we learn about wind, the better equipped we are to navigate the future, to harness its benefits and mitigate its risks in a world that is warming and changing. Reflections on wind. Wind is the breath of the planet, ever present and essential. Wind is more than a physical phenomenon. It is the circulation system of Earth's atmosphere, redistributing heat, moisture, and energy. It is the breath of the planet, inhaling over oceans, exhaling over land, breathing in cycles daily, seasonally, over years and epochs. Without wind, temperature differences would become extreme. Tropics would bake while poles froze even more. Rainforests and deserts would not exist as they do. Life has evolved in partnership with wind. Plants depend on it for pollination and seed dispersal. Animals navigate by it, feed on what it carries, and shelter from it. Humans have built civilizations with an understanding of wind, using it to sail, to grind grain, to generate power, to predict weather. Wind is invisible, intangible, yet it shapes everything. To feel the wind on your face is to connect with one of Earth's most fundamental forces, a reminder that we live within a fluid, dynamic atmosphere, constantly in motion. Every breeze carries stories from distant places. When the wind touches you, it has journeyed, perhaps from far away. It may have begun over a tropical ocean, warmed and moistened. It may have swept across a desert, dried and heated. It may have descended from a mountain, cooled and calmed. Within the air are molecules that have circled the globe, that have been breathed by countless others, that have risen and fallen through layers of the atmosphere. The wind carries dust from continents you will never visit, pollen from flowers you will never see, moisture from rains that fell 1,000 miles away. Each gust is a traveler, a messenger connecting places and times. To be mindful of the wind is to sense these connections, to realize that the air moving past you is part of a global system, a planetary circulation that knows no borders. You are part of this flow, breathing the atmosphere, adding your warmth and moisture to it, participating in the great exchange. Wind reminds us that the world is interconnected and dynamic. In an age of boundaries and divisions, wind teaches a different lesson. It does not respect borders. A storm in one hemisphere influences weather in another. Pollution released in one country drifts to another. Seeds, spores, and species travel on currents beyond human control. Wind is a force of connection, linking ecosystems, climates, and lives. It also reminds us that nothing is static. Air is always moving, always seeking balance, always responding to changes. This dynamism is life's foundation. Stagnation means decay. Motion means renewal, growth, adaptation. Wind embodies change, carrying the new, removing the old, ensuring that life does not stagnate but continues to evolve. In feeling the wind, we feel change itself, the constant flux that defines existence on a spinning, sun-warmed planet. Wind carries both gentleness and fury, teaching humility. Wind is not one thing but many. A gentle breeze can soothe and refresh, rustling leaves in a way that calms the mind. The same air, moving faster and driven by greater forces, becomes a gale, a hurricane, a tornado, capable of destruction beyond human power to resist. This duality teaches humility. We do not control the wind. We can harness small portions of it, predict it sometimes, shelter from it. But ultimately, wind does as it will, shaped by forces planetary and solar, by physics indifferent to human concerns. Storms come whether we are ready or not. Calms fall when we need wind. This is not cruelty but nature. Wind teaches us to adapt, to prepare, to respect forces greater than ourselves. In our technologically advanced age, it is easy to forget our limits. Wind reminds us, stand in a gale, and you feel smallness. Stand in a soft breeze, and you feel grace. Both come from the same source. Listening to the wind can be a form of meditation. There is a practice, simple and ancient, of just listening. Sit or lie down, close your eyes, and focus on the sound of wind. In trees, it rushes and whispers, a sound that is both random and patterned. Against buildings, it moans or whistles. Through grasses, it hisses softly. Each surface, each obstacle, each opening gives wind a different voice. Listening to wind is listening to the invisible, attending to something you cannot see but only feel and hear. It is meditative, pulling you into the present moment. Thoughts drift like leaves on the breeze. Worries fade. There is only the wind, the sound, the sensation. Cultures around the world have recognized this. Monks in monasteries, hermits in deserts, farmers in fields, all have found peace in the wind's presence. It asks nothing of you. It simply is. In a world full of noise and distraction, wind offers something pure, the voice of the atmosphere, speaking without words. The wind connects us to the atmosphere we often forget. Most of the time, we are unaware of the air around us. It is invisible, odorless when clean, taken for granted, but wind makes the atmosphere tangible. When it blows, we feel the presence of air, its substance, its weight, its movement. We remember that we live at the bottom of an ocean of air, a thin layer wrapped around the planet, held by gravity. This atmosphere is precious, fragile. It allows life as we know it. The wind, in making the atmosphere noticeable, reminds us of its importance. It reminds us to care for it, to consider what we release into it, to protect it from harm. Feeling the wind is feeling the life support system of Earth in motion. Every breath we take comes from this envelope of gas. Every gust, every breeze is part of the system that sustains us. In moments of stillness, when no wind blows, we might forget. But when wind returns, we remember. We live within the atmosphere, dependent on its health. Closing Thought's wind is both ancient and eternal, older than humanity. Wind has blown since Earth first had an atmosphere, billions of years ago, when the planet was young and its surface molten. Gases released from volcanic activity formed the first atmosphere. As Earth cooled and the sun shone upon it unevenly, winds began to blow. They have never stopped. Wind shaped landscapes before there were plants to hold the soil, before animals to feel the breeze, before humans to name it. Wind was here when the first life emerged in ancient seas, when the first creatures crawled onto land, when dinosaurs walked, when mammals rose, when humans appeared. We are newcomers to wind's story. It has blown through epochs beyond imagining, indifferent to the life forms below, simply following the physics of heat and pressure. Yet, it has also been a partner to life, enabling the spread of organisms, moderating climates, making the planet habitable. Wind is older than us, and it will persist long after humanity is gone. It is humbling and comforting both. Tomorrow, the wind will blow again, continuing its endless journey. Tonight, wherever you are, the wind is moving. It may be still where you lie, a pocket of calm in the restless atmosphere, or it may be gusting, rattling windows, swaying trees. Elsewhere, it is doing something different. Over oceans, it is raising waves. Over deserts, it is sculpting dunes. Over mountains, it is creating eddies and waves. In the tropics, it is feeding a growing storm. Near the poles, it is howling across ice. Tomorrow, the wind will blow again. It will carry seeds, scatter pollen, push clouds, dry laundry, fill sails, turn turbines, cool the warm, and challenge the cold. It will be both friend and foe, gentle and fierce, silent and roaring. It will continue the work it has done for eons, moving heat and moisture, seeking balance in an imbalanced world. You will wake, and the wind will be there, maybe unnoticed, maybe impossible to ignore. Either way, it will blow. It always does. The wind invites us to pause, to feel, to remember we are part of nature. In our busy lives, we often rush from task to task, enclosed in buildings and vehicles, insulated from the natural world. Wind, when we notice it, pulls us back. It touches your skin, moves your hair, fills your lungs. It cannot be ignored when strong, and even when gentle, it is there if you pay attention. To feel the wind is to reconnect with something elemental. You are a creature of earth, standing on its surface, surrounded by its atmosphere. The wind that touches you has touched oceans and mountains, forests and cities. It has carried the songs of birds, the scents of flowers, the dust of deserts. It is ancient and immediate, global and intimate. Pausing to feel the wind is an act of presence, a momentary acknowledgement that you are not separate from the world, but part of it. The boundary between you and the atmosphere is permeable. You breathe it in. It surrounds you. You are, in every breath, exchanging molecules with the wind. You are part of the flow. And so, as we close this journey through wind and its wonders, may you find peace. We have traveled far together, through science and story, from the smallest breeze to the mightiest storm, from ancient myths to future technologies, from the surface of the earth to the edges of space. Wind has been our companion, our subject, the thread connecting each idea. But now, it is time to rest. Imagine yourself lying in a quiet place, perhaps a meadow with tall grass swaying gently, or on a beach with a steady sea breeze cooling your skin, or in a sheltered valley where the wind is just a whisper in distant trees. Feel the air moving around you, soft and steady. It carries away the day's tensions, the worries, the noise. Each breath you take is part of the wind's endless cycle. You breathe in, and the atmosphere enters you, bringing oxygen, bringing life. You breathe out, and you return it, changed but continuous. In this exchange, you are participating in something ancient and vast. You are part of the wind's journey. Let your body relax completely, releasing into the surface beneath you. Your muscles soften. Your mind quiets. The wind outside continues its work, tireless and patient. It needs no rest, but you do, and that is good. The wind will still be there tomorrow, and all the tomorrows after. It will blow across fields and cities, oceans and mountains. It will carry clouds and clear them away. It will bring rain and take it elsewhere. It will turn turbines and fill sails. It will scatter seeds and lift birds. The wind's work is never done, but yours, for now, is. You have learned, you have listened, you have felt the presence of this invisible force that shapes our world. Now, let yourself drift, like a leaf on the breeze, floating gently downward, spiraling slowly, coming to rest softly on the earth. There is no need to hold on to thoughts. Let them pass like clouds in the sky, pushed along by gentle winds, drifting away into the distance. Your breathing slows, deep and even, like the slow respiration of the earth itself, breathing with the seasons, with the centuries. The wind has carried you through this journey, and now it carries you toward sleep, toward rest, toward dreams. In your dreams, perhaps you will fly on the wind, soaring like a bird, feeling the lift and buoyancy, the freedom of weightlessness. Or perhaps you will simply rest, deeply and peacefully, while the wind stands watch outside, its ancient song a lullaby as old as the planet. The world continues to turn, the sun will rise and set, the atmosphere will flow, the wind will blow, and through it all, you are safe, you are held, you are part of this beautiful, dynamic, ever-changing world. The wind asks nothing of you now, but to rest. So rest. Close your eyes if you haven't already. Let go of the day. Let go of tomorrow. There is only now, this moment, this breath, this gentle presence of air moving softly around you. The wind whispers its final lesson, that life is motion, and motion is life. But within motion, there is also stillness, the calm at the center, the eye of the storm, where all is peaceful. May you find that stillness now. May the wind carry away all that troubles you, leaving only calm, only peace, only the deep, restful quiet of sleep. The wind will continue its journey without you for a time, circling the globe, dancing with oceans and mountains, playing with leaves and clouds. And when you wake, refreshed and renewed, it will still be there, ready to greet you, to fill your lungs, to remind you that you are alive, that you are part of something much larger than yourself, something ancient and ongoing, the great flowing breath of the earth. But for now, sleep. Rest in the knowledge that the wind is always there, always moving, always connecting, always renewing. You are part of that flow. You are part of the wind's story, and it is part of yours. Together, we all move through time, through space, through the atmosphere that holds us. And in this movement, there is beauty, there is wonder, there is peace. Good night. Sleep well. Let the wind carry you gently into dreams, and may you wake tomorrow feeling light, refreshed, and ready to feel the breeze on your face once more, to take a deep breath of the moving air, and to remember all that you have learned about the invisible force that shapes our world. The wind is still blowing somewhere, and here, in this moment, all is calm, all is well, all is as it should be. Rest now, and let sleep come naturally, softly, inevitably, like the wind itself, flowing where it will, gentle and persistent, until consciousness fades and dreams begin. If you are still awake, that is perfectly fine. There is no pressure, no rush. Simply continue to breathe, to relax, to let yourself be. The wind does not hurry. It moves at its own pace, sometimes fast, sometimes slow, but always purposeful in its way. You, too, can move at your own pace into sleep. It will come when it comes. Until then, rest here in this peaceful state, this quiet awareness, this gentle acknowledgement of the wind and all it represents. The atmosphere embraces the planet, and sleep will embrace you. When you are ready, when your body and mind have released enough, when the moment is right, the wind knows patience. It has blown for billions of years and will blow for billions more. It does not worry about time, neither should you. Simply be, simply breathe, simply allow. And when you do fall asleep, whether now or later, know that you have spent this time well, learning about one of nature's most fundamental forces, connecting with the world around you, and preparing yourself for rest through understanding and wonder. The wind has been your companion on this journey, and it will continue to be your companion in life. Invisible but always present, silent but always speaking to those who listen. May your dreams be peaceful. May your sleep be deep. May you wake refreshed and ready to face the wind once more, whatever form it takes, whatever direction it blows. You are equipped now with knowledge, with understanding, with appreciation for this ancient force. Carry it with you into sleep, and let it shape your dreams as wind shapes the world. Good night, dear listener. Rest well. The wind watches over you, and so do we. Until we meet again for another quiet exploration, another gentle journey into knowledge and rest. Sleep peacefully, breathe deeply, and trust in the natural rhythms that govern all things, including the wind, including sleep, including life itself. The wind is blowing, you are resting, all is well. Good night.